I cannot see anything.
Hello everyone, we're group 1 for the Air Design 2 class, and this is our critical design review. I'm Gage Jones.
I'm Cam.
I'm Deep.
I'm Logan.
I'm Dylan.
I'm Sean.
I'm Nick.
I'm Zach.
So we're going to go over a few requirements and objectives for our competition. So we're going to be building a remote control aircraft capable of completing 3 laps of a designated track as shown here. The aircraft must be able to fit into an 8-foot by 8-foot square with a max weight of 55 pounds, and the aircraft must be electrically driven with an OTS battery and motor. So now we're going to go into our initial estimations.
All right, so the gross takeoff weight. So the typical weight values for all the RC aircrafts that we studied and kind of looked up was around 7 to 9.5 pounds. So a rough estimate of 8 pounds was used as our takeoff weight. Because we used the chosen method of composite manufacturing to make our entire plane, it's really difficult to predict this weight accurately. This is because the matrix and the fiber density both need to be known. And because we're using wet layups instead of like pre-impregnated layups or infusion layups, it's also a little difficult to determine this weight. As you can see here, this is our main wing layup. Yeah, it's a female mold with a male mold and carbon fiber wrapped around the male mold and backing back.
So for the power of the motor, we want our aircraft to be somewhere between a sports plane and a trainer plane. So we want to have some maneuverability, and the more power we have, the more control we have over how quickly we can turn. So the motor we selected has about 830 watts of power. That is from the manufacturing spec sheet, and we won't be giving it full thrust all the time. So on average, we'll have about 500 to 620 watts of power being fed. Since we estimated the weight of the plane is about 8 pounds, so that gives our power to weight ratio to be somewhere between 130 to 170, and that meets our requirements to be between the trainer and sports or aerobatic planes.
So because of the track, it's quite long. We estimated it's going to be about 5 minutes. So we're going to need a lift to drag ratio that accommodates for that. And since we didn't have much data of our plane, we extrapolated data from single engine aircrafts like the Cessna 170 or the Cirrus SR-22. And then that gave us an estimate of about 12 to 1 for the lift to drag ratio.
So the process that went into our airfoil selection was the specification that we needed to generate a lot of lift at lower velocities because we have obviously a model plane. We're not going to be traveling at the velocity of, say, a commercial aircraft. So in that case, we selected the NACA 4412. This specific airfoil has a very high camber, which allows us to generate that sufficient lift at our velocity specification. And one of the main focuses of this airfoil selection was to focus on sufficient pilot control. So if we can generate a lot of lift, we'll have lower stall velocities, and it'll be easier to control the aircraft during specific maneuvers like takeoff and landing as well.
Yeah, so then for the wing dimensions, the span and the chords are basically chosen for the planform area to be large enough in order to generate enough lift in order for a takeoff, and then also straight and level flight. And then also shows the aspect ratio to get be long enough to lower drag, but also not be too long to put too much stress at the roots. So this is chosen to be around 6 based on common RC plane aspect ratios. And then planform geometry, we decided to do a taper to kind of mimic the ideal elliptical lift distribution. And then we also have the leading edge swept back. This also kind of reduces drag a little bit more, but at the expense of some lift since the leading edge is now not perpendicular to the airflow. And then we also have a 2-degree incidence angle. This is also just to get a sufficient lift coefficient based on the airfoil plots needed for again, takeoff and straight level flight so that the plane isn't pitched up too much. And then we originally had some twists, but decided not to go through with it due to manufacturing simplicity. And then we also have a high wing configuration. This just adds to lateral and directional stability. And then we also have winglets at the end. This is again just to reduce the induced drag by reducing wingtip vortices.
So yeah, now we're going to go into our fuselage design and more into our propulsion system as well. So for the design of our fuselage, we designed it in order to support the internal mounting of our battery, our motor, servos, and the electrical routing for each of these components as well. We're going to be utilizing a carbon fiber skin reinforced PLA structure for the fuselage in order to give it enough out of plane stiffness to hopefully resist some of the shock loads coming from a perceived crash. So we've decided that there's going to be a 6-inch diameter for the fuselage. This is from our CADs going to be enough to house our battery and our motor and the routing for each of it, and as well as allow you to actually get a hand in there in order to route these components as well. The fuselage is also broken into multiple pieces so that it can have quick assembly and quick maintenance on the plane, given that there is an issue.
So for the motor selection, we had certain requirements that the motor had to meet. We wanted at least 650 watts of power, regardless, to ensure that our plane can fly and have a good enough power to weight ratio. It should be compatible with the equipment we have in the lab, and as all things on a plane, it should be lightweight. It shouldn't weigh too much and shift the center of gravity. And we chose brushless motors because they've been shown to work better for RC planes than other types of motors. So we ended up selecting the Tempest 2820 840 kV brushless motor, as it was the most cost-effective choice, which gave us all the specs we required for this project.
So for our propeller, we ended up going with the APC 18x8E, which is actually quite large, and it could cause a ground clearance issue. We'll see later how we mitigated that. And as Ishan said, we used the, we need a very high thrust, so that's why we chose the large motor. And this one specifically is quite useful to use with brushless motors because it has adapter rings, which is well suited and has a good compatibility with the brushless motor.
So we chose a puller type design because, as I said before, the prop is pretty big and we want to ensure that there's no prop strike. And our reason too was because it has a shorter takeoff distance with its naturally nose high attitude. It will tend to have like a shorter takeoff distance, obviously. And then as the pilot, I need to consider the higher ground stability that tail draggers have because of the forward CG. And this will mostly be evident in the takeoff of the aircraft. I'll have to make sure there's proper rudder control to make sure it stays in line with the runway. And as far as flight characteristics go of tail draggers and tricycle planes, they're pretty much the same.
So for the front main landing gear, we decided to go with a leaf spring design, as this is easier to manufacture than say like a pneumatic one that would require like hydraulics. In addition, the material used was aluminum 5052, which is easier to manufacture. It's strong, light, and cheaper. We went with a thickness of 0.065 a leg length, which is measured from the center of the fuselage, the center line of the fuselage, all the way to the wheel, of 7.93 inches, and it had a vertical height of 4.67 inches. Now, we wanted to make sure that upon landing that the propeller does not strike the ground. So with that, that's why we had the height set like that. And then for the deflection, that was measured without a gusset implemented. And it was assumed that the plane landed simultaneously on both wheels, so that way the load was distributed evenly between the two. And that deflection without a gusset was estimated to be 0.03725 inches. Now with the gusset, it's going to improve the stiffness and reduce this deflection, which will ensure that the propeller will not strike the ground upon landing. Now for the rear landing gear, we just decided to use a pre-made, pre-assembled tail wheel assembly that was made from carbon fiber. And then for both the mounting methods, we'll be using an epoxy adhesive. We decided to go against drilling into the carbon fiber, as this will fracture the fibers and cause the temperature to rise, which will separate the resin from the fibers, weakening the structure itself. And for both the main landing gear and the rear landing gear, we decided to use rubber tires as compared to foam tires. The rubber tires will help absorb the landing impact better than foam tires, which will ensure we do not have a prop strike upon ground landing. Also, sorry, the deflection was also measured or calculated with a landing of 2 Gs. So we went above. We wanted to ensure that we have over a set of range of loads.
Now we're going to go into a little bit more of our structural analysis.
All right, so as mentioned previously, we're using carbon fiber reinforced PLA for almost every manufactured part that we're using. And that's mainly because of its good structural stability in any type of hard maneuvers that we're going to do in the air. And also in case of any unforeseen incident that we end up crashing, its stiffness is going to cause very little damage compared to without carbon fiber. So that's basically why we chose it.
So for this given material, we're going to want to see pretty much if our architecture is going to be able to withstand the 4 different loadings that could happen on our aircraft. And this will be the thrust, the drag, the weight, and the lift. And these loading cases will be distributed throughout the multiple sections of the plane. And these resultant forces will essentially cause either normal or shear stresses, which will be analyzed in the next slide. But essentially, these are some possible loading scenarios we can have. We're going to have a lift force acting along the wing, shear forces also acting along that wing, which we calculated. And then we're going to have moments about all these axes as well, including the wing, the tail, and even the fuselage. So we're going to see how those forces resulted in stresses.
Yeah, so for the stresses on the wings, basically the lift was estimated as elliptical, and then this lift equation was then integrated to get the shear force and bending moment diagrams. So naturally, the largest amount of shear force and bending moment occurs at the roots. And then for the normal stress, we estimated this would occur at the surface of the wings. So then this is estimated from the bending moment, and it's estimated to be 136 megapascals, which is far less than the carbon fiber yield strength of 3 to 7 gigapascals. And then the shear stress is estimated to be more toward the center of the cross section, and this is estimated to be 0.22 megapascals, which is once again less than the foam shear strength of 0.8 to 1.2 megapascals.
Yeah, so just going into a little bit more of why we use composites. So the wings are utilizing a carbon skin wrapped around high density foam, and the fuselage is using a carbon skin with a reinforcement of PLA on the center. Carbon allows for a higher specific stiffness than a 3D print in the fiber direction. So it'll reduce that means that it'll reduce the deflection in the wings since we're using a 2x0 biaxial layup schedule. The foam in the PLA would provide the shape and the compressive stiffness of the wings and the fuselage. The carbon will also be able to hopefully react to the impact loads, putting the failure points at joints and bonds in order to reduce the time to repair post crash incident. And the carbon would be able to react to any kind of out of plane loads or deflections on the wings given the lifting scenario or crash scenario. So now we're going to go into a little bit more of our tail design.
Yeah. So for the tail configuration, we went with the conventional tail design because we had a single and round tube fuselage. As you can see, there's all the different types of tail designs here. And because we're using carbon fiber and bonded joints, we wanted to make this easy to manufacture. We wanted to have good stability in the pitch and roll. And directional, I guess, which isn't really there. And then we also only wanted to use 2 servos with the opportunity of 3 if we needed it. So the conventional was just the easiest to manufacture. The simplicity was nice, and it was easy to bond onto the fuselage as well as provide the required stability that we needed. This is also Nick.
So since the tail provides a force behind the CG, the stability contribution from the tail is really important. So we performed the calculations to figure out what's the best place to have the center of a tail, and we found out it was 0.7 meters behind the center of gravity. This also helps with pitching moment calculations, and the battery is a big weight in the fuselage, which also affects the center of gravity, so we can find an adjustment between where the battery should be positioned to get the maximum efficiency of this plane. For the sizing of the tail, the contour effectors that are situated within the tail need to be made in such a way that the contribution from the deflection has enough stability effects. So we just use a calculation as a guide and then dimensioned our tail accordingly. And there's some pretty pictures that help with understanding.
All right. So as Ishan was saying, the control effectors that we used, we had two main methods of sizing those surfaces. We used a NASA technical document, NCC 2-236, which essentially used common aerodynamic and stability and control theories to achieve the velocity at takeoff. And as you can see, I just kind of took a few screenshots from that technical document. And with the incidence angle, the downwash, and the angle of attack with the wind, they used the aerodynamic principles to essentially find the surface area that the horizontal tail needed to be. And from there, they back calculated what the control surface effector size needed to be. So we used that document as well as a database of RC aircraft and typical sizing guidelines that other RC aircraft manufacturers used, which is in the next slide right here. So this database of RC aircraft and the typical sizing that they used, basically for what Ishan and the rest of the group was saying at the beginning of this presentation, we wanted between a trainer and a sports plane. So we used that database of all those kinds of different designs. And we found that the surface area of the aileron should be 10 to 15% of the total wing area. Surface area of the elevator should be about 15 to 25% of the horizontal tail. And the rudder should be 15 to 25% of the vertical tail. As you can see in the summary, the NASA document and the RC form provided pretty close results. So we added a factor of safety because we wanted to be maneuverable and have good pilot input. And that is what we ended up with for our control effector sizing.
So for the servos, we'll have a total of 4 servos on this aircraft. 2 of the servos will be located by the ailerons, and an emphasis will be made to make the servos be 90 degrees to the hinge line. This will make sure that the range of actuation of the servo will be full and proper, and we will also place the servo as close to the hinge line as possible. This will make sure that the servos have to use minimal amount of power to actually actuate the aileron. And then for the rudder and elevator, we will have these servos located at the root of the vertical and horizontal stabilizers. This is so similarly to the ailerons and the hinge line, it will allow it to have a less struggle to actuate the actual control surfaces. And then to attach the control surfaces to the servos, we'll use a push rod to connect them.
All right, so now we're going to go into our stability and control. So for the longitudinal stability, as you can see, there are essentially 3 main contributors to the longitudinal stability of this plane. On the top right, you'll see the equation for CM alpha that includes the wing, the horizontal tail, the fuselage, the nacelle, and the normal force of the propeller. However, we don't have nacelles, and the normal force of the propeller is taken as negligible. So for the wing contribution, it's 0.019-ish radians, 1 over radians. Horizontal tail, you can see it's negative 0.23, and the fuselage is 0.0028. So our contribution from the fuselage overall is there. However, it's very, very small. And we used a MATLAB script, or sorry, a Python script to calculate this. And changing the center of gravity only really changes the wing and the horizontal tail. And what we found is that our plane does produce a nose down response to any disturbance, and it gives ample stability and responsiveness, which ultimately is very dependent on the CG. So we'll have to be relatively careful when placing that in our plane.
Yeah, so then for the directional stability, it's once again a factor of from the wings, the vertical tail, the fuselage, we don't have nacelles, and then a small contribution from the propeller. So in the wings, again, since they have that high wing orientation, they add a little bit of directional stability, and then obviously the vertical tail adds the most directional stability, as this is the purpose of it. So it is able to respond to any disturbances. And then the fuselage decreases the stability the most, as you know, again, it's this large structure that isn't shaped to respond to the disturbances in the same way. And once again, the propeller adds that a very small amount of stability. So then the overall directional stability ends up being positive, so the plane can be deemed directionally stable.
So lastly, for static stability, we're going to talk about lateral, which is roll. And for this form of stability, we're going to want the roll moment derivative to be negative. This essentially means at a given side slip angle, when the plane is going to naturally roll right, and we're going to want it, if it's stable, to roll back left. And so again, that requires negative for the roll moment derivative. Basically, the contributions to this derivative come from the aspect ratio of the plane, the wing tips, the wings themselves, the horizontal tail and the vertical tail. And for example, at a given angle of attack, say alpha equals 5, we do see that the culmination of these roll moment derivatives are less than 0, meaning that we do have lateral stability. We did calculate this value for all angles of attack, and we found that for any values of angle of attack above -3 degrees, we do have this roll stability that's positive. And so essentially, when we're flying, we're going to want to make sure that we try to stay at least above -3 degrees for the angle of attack.
So this is the dynamic stability section of our plane, and essentially there was a MATLAB state space implementation, and as you can see, it's listed many assumptions. However, when putting in all of the different eigenvalues, when analyzing the outputs of all the eigenvalues from the matrices, we found that the Dutch roll moment was favorable, as well as the short period and phugoid response. So we were concerned a little bit about the short period. However, because it's very dependent on the pitch moment, like I was saying earlier, the center of gravity is also important. And after talking with a stakeholder, Tao, we determined that the center of gravity moving up is only favorable. So we're going to try to make sure that the center of gravity is a little bit above the aerodynamic center of the wings. And that should basically give ample stability everywhere, including dynamic stability.
Just to add real quick, some of the assumptions we made were we decoupled. So roll, the lateral and directional stability are coupled, but we went with the assumption of decoupling them to make equations easier. So it's more linear, and we don't have to solve a nonlinear equation just to get a stability requirements.
Right, so I'm going to stand by the computer for a second here. Now we're just going to go over some of the pictures of our CAD models as well as manufacturing. So this is the side view of our plane. As you can see, the proportions are pretty well there. This is a kind of rear isometric view of it. Everything that is in this photo has been manufactured. The layups are still waiting for the fuselage and the winglets, and then assembly should happen relatively soon, within a week or two. And this is the top-down view. This CAD model still needs to be updated because, as Nick said way back in the beginning, the leading edge swept wings are manufactured. However, in the CAD, it's trailing edge swept. So essentially, after doing some analysis, we determined that the trailing edge sweep was unfavorable for any kind of stability. And to get that elliptical distribution from RC forms and from airplane manufacturers, a leading edge sweep is way more stable and responsive to, or less responsive to side slip angles. So as you can see, that's the leading edge sweep in the wings that we hot wired out of high density foam core. And then these are the high density foam core wings for the tail, pre-layup. All of these have been laid up. So I believe this is the carbon before we put the matrix on. And the method we used was essentially a flat plate layup that we put the wings onto the carbon, and then we took the carbon, folded it over the wings, put it into the female mold, and then bagged it. And the post-processing is going to occur sometime later this week.
And then this is a picture of the landing gear so far. To make both cutouts for the gusset and like the outer layer of it, a water jet was used. And then Gage welded 4 corners together. We didn't want to weld the gusset completely to the outer surface just yet, because we want to make sure that it fits the fuselage. Once that's done, we're going to bend these ends right here to mount the wheels.
That's it. Any questions?
Thank you.
All right, guys. Let's see. First thing I'll say, because I know Tim will say it if I don't. Add slide numbers to your presentation. That'll make it the review process easier. Can we flip back just a couple of slides where you had the top-down view?
Sure.
What are the nubs I'm seeing under the wing?
Those are the wheels.
Oh, those are the wheels. Oh, okay. All right. So, from a construction standpoint, I was wondering what is the internal structure of your vehicle, and maybe I'm still partially wondering that until you got to the very end when you said here we're hot wiring the foam as the inner surface of the wing. Because earlier on you mentioned that you're like wrapping plastic, assuming 3D printed plastic with carbon fiber. And I assumed that was applicable to the whole design until rendering it, right? So as a structures guy, I want to see details of how this is being built. The structural analysis that you did of the wing, when you're talking about the loads being carried in the wing, I'm wondering like what is the structure of the wing that's carrying those loads, right? And it sounds like you're actually loading the wing skin, and that it's like a sandwich composite, carbon on foam. So given that you're loading the wing skin and you have a single layer of carbon fabric, presumably a single layer of carbon fabric as the top skin of the plane, that's under significant compression load and it's awfully thin, right? So how is it most likely to fail?
Given we assume that since our highest moment is going to be at the bonds, it would most likely fail at the bonds. However, we're using Loctite Hysol.
When you say at the bonds, where's it bonded?
So it's bonded in the wing itself. It's going to be joined as one, and then there's a 6-inch diameter cutout in the wing that is bonded onto the actual fuselage.
Okay, so you have, but the top skin of your wing is like continuous skin, and then it's sort of somewhat cylindrical cut out of there and bonded to the sides of the fuselage.
Yes.
Okay. So again, the top surface of your wing is in compression. Right?
It's in compression,
and
so
it's a very thin single layer fabric. How is that going to fail?
On the top skin, the carbon would fail in compression there.
In how?
When it's loaded up from the wings, your wings are bending upwards.
Yeah.
So it's putting your top layer of carbon in compression.
Mm-hmm. And what's going to happen to that carbon in compression?
It's going to wrinkle.
It's going to buckle. Right?
Buckle, yeah.
Right. So what you have preventing that is if it's bonded to the foam, right? And so that's supporting it against buckling, but I'd like to see, you know, some consideration of that as a failure mode. All right, so now let's talk about the lower surface, right? So now you've got carbon compression. Single layer of carbon is going to be better in tension. It's going to be compression. Where does that tension load go in your fuselage? Like what's underneath the fuselage to carry that load somewhere?
So in the central area of the fuselage where the wings are bonded, there's a rack that's a 3D printed like supports in the center of the fuselage, which is also used for mounting our battery that would connect both sides of the fuselage.
So that structure I want to see to be able to evaluate, like, okay, if you're assuming your load is going in there, right? You say, okay, I'm going to do a bending calculation and say, you know, MC over I, what's the moment inertia of cross section of the wing? If you're accounting for the skin as contributing to the cross section of the moment inertia, you've got to have a load path for that load to go somewhere. Otherwise, you're going to be, you know, if the connection to the fuselage is floppy, right? Like if it'll squeeze in and out without any significant load for that amount of deflection, then you're going to carry all of your load just through bending right at the top of your wing. It's not going to be particularly strong in that mode. So I want to see what's inside the fuselage. So like I get a sense of what those load paths look like. Let's see. You talked about when you're talking about your strength analysis. You were talking about no wait. I'm sorry. This is I think when you're talking about landing gear. Yeah. You said you had 0.03 inches of deflection on the ungusseted landing gear. Correct. And you said, oh, we're worried about the.
Sorry, that was with the gusset.
That's with the gusset. Oh, okay. Okay. What was it without the gusset?
I believe it was somewhere on the marks of like an inch.
An inch. Okay, so that's significant, right?
Yeah.
But you had what you described as a leaf spring design, right? And now with these gussets, it looks a lot less like a leaf spring, right?
Yeah.
Like, were you counting on compliance to reduce landing loads, to improve, you know, handling characteristics for your pilot?
It's not something that we took into account too much, and it's also bonded at that structure in the middle of the fuselage. It has supports on either side.
Yeah.
So somewhat of a sharper landing. We believe that the fuselage would be able to handle those loads.
Okay, so that again brings me to a similar question as my wing, right? What is the structure internal fuselage? Where does that load go into? One thing I like that you did, and you didn't have it on your slide, but I think like I saw, like, I forget who's you was talking about this. I mean, yeah, so I saw like light bulb going, oh, I should talk about the load kits, right? So you said, oh, we analyzed for a 2G land. So I appreciate you saying what was it?
Yeah.
Okay, yeah, I appreciate you saying that, because like I always want to know, right? As an instructional analyst, you can tell me it's, you know, got a factor of safety, or it's got margin, or whatever you want to tell me, but like what load case is that, and like does that make sense that that's a critical load case for your structure? So good job on that. On the, I think the next slide, we're talking about the wing loads.
Oh, yes, sorry.
Yeah, that is a little bit, yeah. Here we go. Okay, so what's going on with your shear force equation, your moment equation? I don't recognize a lot of those variables.
That was just okay. So this is integrated from a elliptical lift distribution.
Okay.
I didn't perform the integration. I plugged it into Wolfram Alpha. So yeah,
Spoken
so
like a true engineer.
yeah. So then essentially, B would be the wingspan. I believe the L naught would be the maximum lift at the roots.
You mean
and
like
then-
total lift of the airfoil, like lift force on the airplane?
So like when you have the elliptical lift distribution, it would
Was that scaled by the root, like load per length, or load per area?
Yeah.
Okay.
Yeah. So then Y is essentially just that the distance along the span. So then
Okay. Okay. I'd like to see like a picture and kind of define the variables.
Yeah.
All right. So on the next slide, we've got, you're telling me maximum normal stress. I don't know, I sort of intuited how you got that once I saw your foam core, right? But I don't see how you got that, right? So show me, you know, we're doing MC over I for bending, and here's the cross section we're using. This is why we think this is where the load path is. You know, I'm sort of used to other teams coming up and they've got more conventional like spar designs, right? So like what's the cross section of spar versus the cross section of the skin, where the load is, and what makes sense to use there. So like those are the lines I'm thinking around for this. And then we've got a yield strength, and to the best of my knowledge, carbon fiber doesn't really yield, right? Yeah. So I know I talked about this in space design class, and so I'll talk about it here too. Typically, when we're doing an analysis, we're going to look at, like for metallic structures, we're going to look at yield failure, we're going to look at ultimate failure, right? And they're going to have two different factors of safety, right? I don't see you telling me what your factor of safety is that you're working to on this slide, but because carbon fiber just doesn't really yield, right? It's a brittle material. Your typical factor of safety is probably 1.5, right? Was that a design requirement, or was that something that you guys?
Typically, we use like 1.5 to 2.
Okay, yeah. So if you're telling me yield is 1.5, that is for aviation, that's conservative for yield, right? Typically, yield would be like 1.1, 1.15. Associated with that is a whole lot of like material control and a whole lot of effort going into defining the loads and whatnot. So, you know, if you told me for an RC aircraft that you're building, you know, in a lab, in a, you know, an undergrad lab, if you told me that we're going to design something to have 1.5 for yield for fit form function stuff, okay, I believe that, right? Because you're not spending millions of dollars documenting, you know, the whole build process. But I would like to see, like up front, here's the factor of safety we're working to, I would expect to see in an aerospace project a margin of safety. Anybody familiar with margin of safety versus factor of safety? I see some heads nodding. Maybe. All right, so margin of safety, right? You take your allowable load, whatever load your structure will withstand for whatever failure mode you're talking about, right? So if we're talking about ultimate, whatever load like physically breaks your structure, that is your allowable load. And then you take the load you expect to see, your design load, multiplied by your factor of safety. You take a ratio between those two things, right? So allowable divided by factor of safety times design load, and you subtract 1 from that, right? So that's your margin of safety, right? So if your margin of safety is positive, greater than 0, that means that ratio is greater than 1, right? So that means that you meet your requirement, right? So you have more strength than you're required to have. If your margin of safety is negative, you don't meet your requirement and you have more work to do, right? So as a reviewer, like I'm looking for what's the margin of safety on your structure. That's specific to aerospace. If you guys wind up in a different industry, there are going to be different conventions, but in an aerospace class, that's the convention we use. Let's see, a couple, again, I apologize because I didn't know what slide this was, but we were talking about the you were reducing your material selection stuff, where you said, okay, here's, you know, carbon fiber in your material selection chart, and I think in the very next slide, yeah, so that one, and yeah, okay, so here, reduces deflection in wing with 2 times 0 sub b. What is that?
That's so we're using a biaxial weave carbon. So it's in the 0 direction. We have 2 plies of 0 direction biaxial carbon.
It's our layup schedule.
Meaning, so is this not a 090 fabric?
It is a 090.
But it's a 090 fabric.
It's
what is it?
It's 2 layers of 090 fabric.
Oh, okay. So are you actually building your wing at 2 layers of?
Yes. Yes.
Oh, okay.
Yes.
Okay. I did not catch that. Why?
So it's for one, we recommend it would be stiffer in order to like react to some of those loads in a more surface level reason. If you have 1 layer of carbon over it, most likely your core would show through.
Okay, so aesthetics. Okay. Were aesthetics part of the design requirements? things can hit. All right, so from a structure standpoint, was it necessary or was it extra?
It was extra.
It was extra.
What's your weight situation? Like,
The-
did you hit your target weight?
Yes,
We're
we
likely
expect-
below our target weight. So.
So it's not as bad. So one of the things I mentioned in my write-up for a previous group is like, if you're going above and beyond, you better perform, right? You better be able to do the minimum before you go above and beyond, right? And so it sounds like this is acceptable from a, if you want to add aesthetics. Okay. Let's see. Then you mentioned that you have some ability to adjust your CG by moving your battery.
Yes.
How much?
We can move our, so by far our heavy, about 30% of our weight of our plane is coming from our battery.
Okay.
So by moving it forward, we, in the range of the battery can go, we can adjust our CG by around ± an inch.
Okay. Where is it, like, at its furthest forward point, its furthest aft point, where's your CG relative to your core?
So as far as I know, I could be wrong, but I believe it's at least 3/4 of an inch in front and then 2 inches behind, because we have that much space. But we don't need the 2 inches behind. It was just, that was part of the, like Gage was saying earlier, the battery, the middle section and the fuselage for the structure, as well as the battery housing. We wanted to extend it so that it had more structure in the fuselage, but we could also move the battery.
Yeah, so I'd like to see when you present this, and you're way more knowledgeable about this than I am, but I'd like to see, where is your CG relative to your chord somewhere in your presentation. I'd like to see, given how much movement you have, physically room to move your battery, this is where we can tune our CG to, right? And I think when you guys mentioned that you feel like you have to be pretty precise in your positioning your battery to get your CG within a tolerable range for like flight dynamic stability, right? So how do you achieve that? Like, is it you're just gonna put it in and check where the CG is by hanging on a string, and if it's not in the right spot, you move it? You have like some defined lines in there that you say, okay, we're gonna line the battery up with line A for test 1, we're gonna line up line D for test 2. Like, how are you achieving that?
So I personally ran like a CFD sim, which is just kind of a baseline from our 3D model. And then from there, I did a moment calculation to find where the CG should be so that it would be neutrally stable everywhere. So we roughly know from manufacturing tolerances where the tip or the top of the main wing's root is, how far from that and from the nose the CG should initially be placed during manufacturing to check. And then from there we can adjust if needed.
That's all I got.
Thank you.
Thank you.
So for me, I feel like the first thing I want to comment on is the presentation. It's the big logic of your presentation slides. It's like you started with like the takeoff growth rate estimation. I mean, the takeoff growth rate is not based on your actual design. You calculate the weight. It's at that stage, like at the beginning semester, it's the first week of semester. You don't have anything designed yet. So it's more based on the history data. You want to do something like similar to whatever existing aircraft. Then you have initial takeoff growth rate. It's not based on you put a picture of it like, okay, we're gonna do carbon fiber. This is like, no, you don't calculate anything. You don't have any design yet. So, and also I feel like, as I said in the lecture of the presentation, I want to see a logic like for the whole presentation, not for each topic, but for your presentation, it's more like scattering information everywhere. I don't see the logic behind it. I mean, you have the initial estimation at the beginning. You have the wind design. I mean, what is the result of wind design? Did you do any simulation like what's the lift drag ratio of your wind design end? And you list what propeller you use, what motor you use. So again, have you any estimation of what the thrust can generate by your actual design? Like, I want to see, like, if you want persuading me that your design gonna work, I want to see, like, okay, this is the initial estimation, this is my design, and based on my design, what is my calculated, like, thrust, anything, to see if it satisfies my initial estimation. And I see like information, like you have the manufacturing information in the tail design, in the wing design, and in fuselage design, and then you have a specific CAD and manufacturing at the very end. I feel like someone need to check the whole logic of the presentation, like to make it like right now. What I feel is like different students maybe make different slides and put together, that's it, done. Someone need to check the whole logic of the whole presentation, and also some slides they are like just too busy. Well, this is I can consider this one of them, but there are also like other slides like the tail size and pictures, and also well you can check the whole size. Some the pictures I feel like again it's different style from different students. Some slides they are really good. Some slides like you try to push all the information in one slide. As I said in the lecture, there's really no constraint how many number of the pages the printed slides you should have. There's no upper limit. Just make it clear. The only constraint is time limitation. So try not to like push all the information on one slide. If you cannot see the secret information again. And also there are like I think it's the landing gear and also the stability analysis. The significant digits, check the significant digit if it's necessary. If it makes sense, you guys are engineers, so you know better than me. And also the and one thing I'm just curious because you use carbon fiber for the fuselage also. I was wondering if it affect the the signal transmission.
Oh, no, it doesn't.
It doesn't. Okay. That's good. So I think we're done. Sorry.
So we have an exam in formal booking in here, so I need to get it.
Well. Thank you.
Good job, Cam.
You.